Alrighty, so here we go again with quantum mechanics. And this time we are talking about matrices. And we'll start off something really simple with how matrices and vectors work together. And then we'll go on with eigenvectors. And this is not going to be that complicated, but you will have to pay attention. But if you watch any of the other videos in this quantum mechanics, you'll know that paying attention is very important anyway. So, matrices. This will become much easier if I use a grid. So let's say we have a grid. We'll call this the y-axis and the x-axis. And I'm actually going to make another layer for this, because this is going to be helpful. So, suppose that we have a vector, which I would call V. What you have to understand is that if we have a matrix and multiply it to a vector, it will equal a new vector, which I will call, in this case, V prime. I'm actually going to use a selection tool for this. So, let's say that I grab all this, and I have this vector. Well, I can apply a matrix to it, for example, by increasing its height. I can make it longer, I can make it smaller, For example, we can draw V prime as pointing in this direction. We can call it that, V prime. The matrix would take this vector and turn it into this vector. But it doesn't have to be one of those. Like V, we can have a vector, say, L. We have a matrix. I might start off pointing in, let's say, this direction. We'll call this L. It can go through a matrix and point in this direction and become L prime. And there's really not much to this. What you have to understand is that matrices can take a vector, you can insert it into the matrix and insert it out, and it creates that, a new vector. Where this is really important is like in computers. So let's say that we have this, a stick figure. And all the hands and feet are actually defined by vectors. So we can have a vector here. I'm actually going to make another layer. So nice that we can use this. We can create a vector here that represents his hand. And we can have another vector here that represents his foot. And another vector, it's hard to see, but it can represent his head. And so we'll call these like H. I'm just going to keep it simple, and we're only going to focus on the hand. So this is the hand vector, and this is the foot vector. So we have H and F. Well, we can actually apply some matrix to both of these, and that will actually give us a new vectors. We'll call them H prime and F prime. And I'm going to show this right now. So if I go into our selection tool and I select our stick figure, we can make him bigger. But I better move him into like the same location somewhat. Just make this easier. Now, as you can see, his hands and feet are no longer in the same place. So we need new vectors to describe the foot. So call this the hand prime. And as you can see, it's not in the same direction as the old hand, you know. And we can also do the same thing with the foot, you know. And as you can see, by applying our matrix that we just did earlier, you know, we can change the shape of our hero. And we can apply any matrix we want, you know, we can make him smaller, we can make him wider, we can make him, you know, I do not know how to do it in this software, but you could theoretically rotate the character. And matrices do all of that. Like when you, or say, even here I'm drawing this, if I move anything, a matrix is applied to all the vectors in that box. Hang on, I better get rid of this. Delete that layer. Alright, so now it's on to eigenvectors. Let's see if I can erase these. This will be the finishing up our discussion on matrices until next time when we talk about the quantum mechanical aspect of it. Although we might have a lot of time, so we'll see about that. Anyway, eigenvectors. As you might recall, we can have a matrix M, and we can combine it with a vector, like a hand vector, and it will create a new hand vector. But what it, you know, and as you might recall, this hand vector does not point in the same direction as this one. But what if we have one that does? An example would be, let's say, the head. You know, I know this looks like hand and head both start with H, which hurts our notation. So let's instead imagine a completely different thing. Let's imagine that we have a triangle, and every point in the triangle is defined by some vectors. You know, for just to stick with them, avoid our losing our sanity, we'll call this V1, and this one shall be L1. We can apply a matrix to these vectors. You know, it'll be the same matrix to V and to L, and they will equal new vectors, which we will call V2 and L2. You know, and so let's do that now, right here. So I will take a matrix. I will actually stretch this vector up somewhat. We'll move that triangle back into position though. As you can see, L2 points something like this. This is L2. And this bit, I'll have to draw around the original vector, but you should be able to tell, is V1. Now I need to hide this triangle. Let's see, that should work. Anyway, you might notice something important here. This vector changed. No, I'm not going to write it. This vector changed its direction because it used to point in this direction, and now it points in this direction. However, this vector did not. It used to point in this direction, and now, well, it still points in that same exact direction. You know, its direction does not change even after going through the matrix. You know, I guess to make it its worldview wasn't changed by the matrix. Sorry, that's a joke. Anyway, what this means is that V is an eigenvector. It doesn't change, its direction. Other vectors like L, they change their direction, and they can point in any direction after the matrix. But V is not. V is. It's an eigenvector. Another example would be the vectors that point to these vertices of the triangle. If we stretch the triangle in any way, these vectors do change. They still point in the same direction, and so these are eigenvectors too. And so we're left with basically 3 eigenvectors under this matrix. And well, I can't really think of anything else to say about eigenvectors except for eigenvalues. I should have add that too. Eigenvalues these are how much it's stretched, I better write this down. How much eigenvectors are or technically squished, because sometimes, like if you have a negative eigenvalue, that means your eigenvectors got smaller. They point in the opposite direction of where they started. But basically, these two go together. Eigenvectors are more important of a concept. And also, you can't have eigenvalues without eigenvectors, of course. But anyway, simply put, the eigenvectors don't change under the matrix, unlike everything else. And eigenvalues, they are how much the vector gets stretched by, or squished by. And this will all be important later with matrix quantum mechanics. It appears I have quite a bit of time, so I'm actually going to try and explain an example. Suppose that we have a particle launcher and a particle, magnets and stuff, which, as you might recall, they can deflect the particles to being either up or down. Hang on, I better use the right colors. Or down. We would say that how should I put this? This bit here, this whole apparatus that sets the spin is like a matrix. No, it doesn't look like a matrix, but it's a bit like a matrix. And this here, when the particles are coming right out, we can call this a vector. We'll call it just V. And over here, we can call these V prime. And now you can maybe see why we had all that bit about vectors. Because if we have, a vector here, it will go through the matrix and get converted into either being up or downward spin. Because, here, V might be a little bit like this or this vector, where it's a combination of both at once. It's an up vector and a down vector all at the same time. But when it goes through the matrix, it will either produce a zero, a 1, 0 vector, which we, for this sake right here, we can call it an upward vector, or it will cost a 0, 1 vector, which we'll call down vector. And this one would be like v prime of 1 and v prime of 2, you know. And so by observing the particle vector here, it's like putting it through the matrix, and then it will spit out either up or down because of the eigenvectors, you know. This is all very helpful for quantum computing, because you can have a system of psi, which is equal to, let's say, 0.75 and 0.75 chance of something of becoming up or down, and you can put it through a matrix, and this would give you psi prime, which should be either, one type of vector or another type of vector. And if you might recall, maybe you don't recall, but in quantum computing, this might correspond to an upward vector, and this might correspond to a downward vector, and this, as you may call, is like a 1, and this is like a 0. And so our quantum computer, it basically takes in some value of psi, which is like a mixture of 1 and 0, and it turns into into either a 0 or a 1. It's kind of similar to like regular computers. You can have something called a NOT gate. Might look a little bit like that. And basically what it does, if you put in a 0, it will output a 1. But if you put in a 1, it'll output 0, and it'll basically put in the opposite of whatever you put in. That's how like a regular computer works. With a quantum computer, you can have a psi, which is equal to, let's say, 1, 0, and you can have a matrix that then converts it into downward 1. And this is very similar to a NOT gate. I mean, it's not the same, of course, but it's very similar. And obviously these matrices play into all sorts of roles, like energy states. You might remember something like acting on a particle can change the outcome. Well, we can have a particle, a vector, which we call the, psi 1 might be equal to 4, 3, and as we, observe it, see that there's like an eyeball. This is like a matrix, which then turns it into psi prime, which might equal some other vector otherwise. Anyway, I'm running out of things to say, to be honest. There's not much else beyond here that doesn't involve dense calculations. I could go in quantum field theory, but we'd have to go through special relativity first. So you know what? Next time, next time, we will not be going over quantum mechanics. In fact, we'll be going over special relativity, the starts of it, and maybe on the side, how to math. Because, I've been showing things like derivatives and integrals and matrices, but without any way of actually calculating anything, and that made me feel bad. So, I'm going to have to add a how to math, how to do integrals, how to do vectors, and I'm also going to next time add a brief intro to relativity. Hopefully, it should be good. Anyway, I'll see you next time.